welcome to this explainer. Today, we are diving into something truly fascinating. We are going to take the inherent chaos of everyday uncontrolled processes and transform them into predictable, high-performing systems. And we'll do this by mastering quality control. Look, whether you're building physical products or delivering a critical service, understanding the math behind your operations is an absolute game changer. So, let's get right into it. Here's our roadmap for today. 1. The core of quality control. 2. Making sense of data. 3. Finding the center. 4. Measuring process capability. 5. Visualizing process control. And 6. The ISO 9000 standard. It's the million-dollar question, isn't it? How do companies actually ensure perfection in every single product or service they deliver? The truth is, without structured data, manufacturing and service delivery are really just guesswork. Sure, you might get it right sometimes, but you won't know exactly why. All right, Section 1, the core of quality control. So quality control, or QC, is essentially a set of procedures meant to ensure that a product or service adheres to a specific, defined set of quality criteria. Now, here's a really crucial distinction. It's similar to, but definitely not identical to, quality assurance. You see, QA focuses on the process of actually creating the product, while quality control assesses the product itself. It uses things like benchmarking and physical testing to track any significant differences. To actually make QC happen, organizations rely on 7 key components. These range from your basic inspection and testing to training and corrective action. But I really want you to pay special attention to number 3, statistical process control, and number 7, continuous improvement. These two are the analytical engines. They're what keep a process running safely within acceptable limits instead of just reacting after a product is already broken. Moving right along, Section 2, making sense of data. Okay, so measurement starts with exactly where our data comes from. Operational data generally falls into 2 main buckets. First, you have primary data, which is collected firsthand. Think of a factory floor manager running a direct experiment or sending out a survey to customers. Secondary data, on the flip side, is gathered from studies or experiments run by other people. Knowing where your data comes from is step 1 to actually trusting it. Once you've got that data, you have to categorize it. Data branches into qualitative, which is categorical or ordinal, like car colors or, say, happiness ratings, and quantitative. Now, quantitative data is what we really love in process management. It breaks down even further into continuous data, like the exact weight of a part, and discrete data, like shoe sizes or the exact number of defects. When you're dealing with discrete data, which is data generated by exact counting, you need a very methodical way to organize it. First, prepare a 3-column table. Order your variables and start tallying. Grouping tallies in 5s with a crossing line might seem a little old school, but honestly, it's a foolproof way to quickly convert raw counts into workable frequencies. And finally, always check your frequency totals against the total number of observations, just to make sure nothing slipped through the cracks. In real-world situations, though, we're usually looking for the bigger picture. And that is exactly where cumulative frequency comes in. It's essentially a running total. So say we collected data on how many hours a subject, let's call her Shreya, watches television across several smaller daily studies. We'd add the frequencies from one category to the next to see her total weekly habits. It scales those micro-observations right up into macro trends. Next up, Section 3, finding the center. We find that center using measures of central tendency, and there are 3 heavy hitters you really need to know. The mean is your standard average, but be careful with it because it's highly sensitive to extreme outliers. The median is the exact middle value when your data is arranged in order, which makes it way more robust against those outliers. And the mode, that's simply the value that pops up most frequently. Check out how these 3 formulas play out with the exact same data set of daily temperatures. By applying the mean, we get 21.86 degrees Celsius. But if we order the data to find the median, we get exactly 22 degrees. And since 22 appears twice, it's also our mode. So you have 3 different calculations giving us distinct, actionable metrics from the exact same raw data. Pretty cool, right? All right, Section 4, measuring process capability. So variability basically happens in 2 ways.
First, we have chance causes. These are normal, inherent variations, just your minor fluctuations in machinery or the environment. When only chance causes are present, your process is in statistical control. But then we have assignable causes. These are specific, identifiable malfunctions, like a broken part or a sudden drastic drop in temperature. When assignable causes enter the mix, your process is officially out of control, and honestly, your quality is ruined.
You can actually see this visually on a drift chart. Over on the far left, the process is centered and perfectly in control. Only those normal chance causes of variation are present. But as time marches forward to the right, assignable causes 1, 2, and 3 are introduced. You can literally see the normal distribution drifting upward, eventually moving entirely outside the acceptable upper control limit. If left unchecked, this is exactly how a process fails. To prevent this kind of failure, we measure process capability. This is a statistical measure of inherent variability that reflects a process's non-conformance rate as a single number. For continuous data, we use metrics known as CP and CPK. For attribute data, like defect rates, we use sigma. In fact, huge continuous improvement initiatives like Six Sigma use these exact estimates at the beginning and the end of a study to quantify the precise level of improvement they've achieved.
Moving on to Section 5, Visualizing Process Control.
This is where the quality control chart comes in. Think of it as your operational dashboard. It starts with a central line, representing the mean of your data. Then we set our boundaries, the upper and lower control limits. These are usually set at plus or minus 3 standard deviations from the center line, establishing a strict baseline of acceptability. Finally, you just plot your data points against a timescale on the horizontal axis. Now, you've got a whole menu of charts depending on what you're tracking, like R, P, NP, C, and U charts, which are great for ranges or different types of attribute data. But the X-bar chart is incredibly useful because it monitors the average of sample continuous data over time. For the X-bar chart, if you see your data points falling outside those plus or minus 3 standard deviation control limits, or if non-random cyclical patterns start developing, your process mean is unstable. It demands an immediate investigation to find those assignable causes.
Finally, Section 6, the ISO 9000 standard.
So, how does all this scale globally? That brings us to the ISO 9000 series. This is a family of international quality management standards designed to help companies document their quality systems effectively. The amazing thing here is that it scales to any size organization and isn't locked to any single industry. ISO 9001, which was first published back in March 1987, is actually the most successful standard in ISO history. It gives you the ultimate framework to satisfy customers and meet really rigid regulatory requirements. And the real-world results? They absolutely speak for themselves. By implementing ISO 9001 frameworks, stuff like document control, auditing, and corrective action plans, a community anticoagulation therapy clinic actually achieved a 100% satisfaction rate among patients and providers. So this isn't just about manufacturing widgets on an assembly line. Applying these statistical controls in healthcare literally saves and improves lives. Which leaves me with this final thought for you. If a community healthcare clinic can hit a 100% satisfaction rate using these exact quality control frameworks, what could tracking the math of your own processes transform in your organization? Whether you're crunching discrete data, finding your process capability, or plotting out an X-bar chart, the tools to eliminate chaos are right there at your fingertips. Thanks so much for joining me today on this explainer, and I will see you next time.